Welcome to the Deep Dive. We're here to unpack the key insights from quite a stack of sources just for you. Now, usually when you think about cosmic change, you're thinking vast timescales, right? Billions of years, geological ages. But what if just sometimes the universe actually lets us watch evolution happening, like over just a few human generations?
It's pretty incredible when that happens. And today, we're diving into this beautiful object called Planetary Nebula IC418.
IC418.
Right, people often call it the Sparograph Nebula. You see why it's got these amazing patterns.
Like a cosmic flower.
Exactly. It's basically, the final glowing act of a dying star shedding its layers. Really elegant.
So our mission for this deep dive, figure out how astronomers use, get this, 130 years of old data.
An amazing amount of historical data.
To actually measure this star changing. And the kicker, this tiny star is poking holes in how we thought stars like it were born.
And this isn't just guesswork. We're basing this on some really solid research, including a new paper in Astrophysical Journal Letters. They genuinely pulled together over a century of observations. Spectroscopy, specifically.
Okay, so let's unpack this. With all that data spanning 130 years, what specific change did they actually see in IC418?
Well, what's really striking is the direct evidence. They found this consistent, steady increase, like by a factor of about 2.5.
An increase in what?
In the strength of certain spectral lines, think of them as light fingerprints. Specifically, these lines called OIA, that's ionized oxygen, compared to another line, HO, which is hydrogen.
Okay.
And seeing those relative strengths change over 130 years, that's like watching the star's thermostat get turned up in almost real time. It's actually one of the fastest non-catastrophic stellar evolutions we've ever clocked.
Wow. Okay, so they see these lines changing strength. That tells us the star is heating up.
Exactly. And using some pretty sophisticated computer simulations, photodization models, basically.
Digital lab.
Right. They calculated the central star's heating rate. And it's somewhere in the range of 15 to 42 Kelvin per year.
15 to 42 Kelvin a year for a star. That sounds incredibly fast.
It is. On cosmic scales, that's like watching a furnace dial itself up right in front of you. It's a rapid change.
So if we know how fast it's heating up, does that tell us more about the star itself, like its fundamental properties?
It absolutely does. That precise heating rate, it let them pin down the star's current mass really accurately, somewhere between 0.560 and 0.583 times the mass of our sun.
Okay, so about half our sun's mass now.
Roughly, yes. And then using these relationships, we have initial final mass relations. They trace back its history.
Like stellar ancestry.
Kind of, yeah. They figured out that the star, it started as its main sequence progenitor, must have been between 1.25 and 1.55 solar masses.
Okay, 1.25 to 1.55 solar masses originally. Why is nailing down that specific original mass so important here?
Because IC418 isn't just any planetary nebula. It's known to be carbon-rich. Its carbon to oxygen ratio, the CO ratio, is about 1.3, more carbon than oxygen.
Which means?
Which tells us its parent star must have gone through a specific phase. It must have been an AGB carbon star. These are old stars known for puffing off outer layers loaded with carbon. It gives the nebula a very distinct chemical signature.
Right, so we've got its current state, how fast it's heating, its current mass, even its starting mass, and we know it came from a carbon star.
Seems like we painted a pretty clear picture.
You'd think so, but here's where it gets really interesting. There's a puzzle, a contradiction, actually.
The plot thickens. What's the contradiction?
Well, that initial mass we just derived, 1.25 to 1.55 solar masses.
Yeah.
That directly clashes with our standard models for how carbon stars are supposed to form, at least around stars with similar overall composition to our sun.
How so? What do the models predict? The models generally say you need a minimum starting mass of about 1.65 solar masses to become a carbon star. Yeah. And for one with a CO ratio like IC418's, around 1.3, you'd expect even more. Maybe 1.8 or 1.9 solar masses initially.
Wait, so the observation the history pieced together over 130 years says the star started smaller than our theories say is even possible for it to become what it is.
Precisely. The star's actual observed evolution is telling us our theoretical cookbooks might be missing a key ingredient, or maybe getting a measurement wrong.
So what does that imply? Are the models just wrong?
It suggests that, yeah, some part of our models might need tweaking. It could be the assumptions about stellar atmospheres, or how we calculate these heating rates, or maybe even those initial final mass relations we use to trace its ancestry. Something's not quite right. It's a really powerful reminder. Observation, especially long-term observation like this, can really force us to rethink things we thought we understood. The universe keeps us humble.
Absolutely incredible. So we started with this idea of seeing cosmic change happen fast, relatively speaking, and we end up with this beautiful nebula, IC 418, showing us its evolution over 130 years.
Yeah, like a little cosmic clock ticking visibly.
Only for that clock to reveal a major inconsistency in how we thought stars like its parent actually come to be, the carbon star formation puzzle.
It's fascinating, isn't it? Even with all our science, all our models, the universe just keeps throwing these curveballs. It forces us to dig deeper, question assumptions.
Makes you wonder, doesn't it? What other processes out there, things that seem incredibly slow, might actually be revealing secrets right now if we just look closely and for long enough? What else is waiting for its own deep dive?